Hi, welcome back to RDBMS and let's build a DBMS. Now, this is where I really get excited. It's fun to build any system. So, if you were told that you are in those 60s where you had only files and we have tons of these other requirements like consistency, inconsistency, redundancy, security, backup, and so on, and we are interested in building a system which would take care of all these requirements, how would you even get started? What would you do? Take a minute and think about it. Well, usually for most first class systems that you see, let's take operating systems for example. DBMS is another example. For many of these systems, the fundamental thing that usually drives the design is the underlying model. So since here we are managing data, we need some underlying model for how to see the data that we have. So first, let's start with this question on what is relational about the relational database management system. So let me take you back to the definition that we discussed. That a database management system is a collection of interrelated data and a set of programs to access the data. Please focus on the interrelated data side of it. So the fundamental idea here that we are about to discuss is the idea of relations. Um, so let me refresh your mind with the concept of relations, which you probably know already. So here is a quiz for you. A relation R from a set A to set B. So I believe you still remember the notion of functions and relations. So set A to set B is a subset of Cartesian product A cross B. True or false? If you said true, you should give a pat on your back, and that's absolutely correct. So let's assume we have two sets, set A and set B. And let's say I have a set of all ordered pairs A cross B obtained from this sets A and B. So which means simply we take each element of set A and associate it or relate it to an element in set B. So we have a blue circle related to blue triangle and a red triangle, and similarly a black circle is being related to red blue triangle and red triangle. So we keep doing this, and if we do this for every element of A to every element of B, then we have a cross product or a Cartesian product. But what we see is that well, the textbook definition, let me first cover the textbook definition. It says that a relation is a subset of a Cartesian product. So any valid subset of this Cartesian product is a mathematical relation. So what's the idea there? We are basically relating one item in one set with another item in another set. Not every association is a valid relation, so we drop some of them. So not every item in a Cartesian product need to be in my relation. So that's the fundamental idea that you should remember. But why are we talking about relations and how are these related to a database? So let's take a look. uh, so let's say I have a set ID which is 1213, and let's say there is another set whose name is name, and it has two elements VB and SD. So let's say these are two instructors at CMI, VV and SD. So a Cartesian product between ID and name would give you, these relations, meaning one is associated with SD, one is associated with VV, two is associated with SD, two is associated with VV, and so on. Remember, we are just doing the same thing that we did with the circles and triangles in the earlier slide. But notice that in reality, we might just want to. There is someone selling some or marketing some product outside. I'm not sure if my mic is picking up that disturbance. But anyway, let's get back to the lecture. So while this is the Cartesian product of ID and name, in reality, some of these might not be valid. So let's say I associate the ID 1 to SD and 2 to VB, then I'm only interested in 2 relations and not the rest of them, right? So in other words, uh, we have a relation um, if we assign a sequential ID in this case, and in general, we see that a subset of a Cartesian product is very useful in depicting interrelated data. So let me take you back to this original definition where we are concerned about interrelated data. So we are capturing the interrelated data as the mathematical concept of relations. When I first read this years back, um, this just took me by awe. Um, the beauty is that such fundamental mathematical ideas, when applied, can have a really powerful impact. In the rest of this course, we'll see how this fundamental idea of relation has been exploited to build a database management system. This idea was proposed by Edgar Cord. He went on to win a Turing Award. If you are more interested in this, you can of course go and read here. In this course, we also discuss a database management system. So we just now discussed about a model to capture the interrelated data as relations, the mathematical notion of relations. Now let's turn our focus to one DBMS. In this course, I have chosen to use MySQL, which is a freely available DBMS tool. Uh, I encourage all of you to go and download the latest version of MySQL. Uh, when you go and download this, remember to download the community version. There are many other versions like the enterprise versions. Please ensure so that you will see a tiny link when you download it. Somewhere down in the page which talks about community downloads. So I have installed a community edition of MySQL for Windows on my laptop. So please go ahead and download the latest version. When you do this, you might have to also install some prerequisites depending on the operating system that you use. Please remember to install them as well. Okay, um, we'll come back to uh, MySQL in the future classes, but now let's turn our attention back to the idea of relations. So let me tease you with a question. So let R be the set of all binary relations on the set 1, 2, 3. Okay, so I have a set which has three elements 1, 2, and 3 in it, and I am interested in creating binary relations. So that means we have ordered pairs um, there. So suppose a relation is chosen from R at random, the probability that the chosen relation is reflexive, rounded off to 3 decimal places, is what? Please pause the video here and try to work this out yourself. Okay, so let's continue discussing this. What is a reflexive relation at the first place? So if set A has three elements 1, 2, and 3, then then if we have 1 related to 1 and 2 related to 2 and 3 related to 3, then such a relation which has all these three relations, right, or three associations, we call that as a reflexive relation on A. In other words, here is an example: 1, comma 1, 2, comma 2, 3, comma 3. So these three must be part of R, and along with that, I could have any number of other relations as well. So now this set is a reflexive relation on A. Now, these set of ordered pairs are also a reflexive relation. You see that 1, 1, 2, 2, 3, 3 exists, and then along with it, I also have 1, 2, and 3, 1. Okay, so these are all these are binary relations, and now we understand what a reflexive relation is. Now, can you work out the probabilities? It should be fairly straightforward. From here, the number of reflexive relations would be 2 to the power of 6, and that's because three elements are fixed, they do exist, but along with these three elements there are some elements which may or may not exist, and there are six of them. Can you find those six of them? I'll leave that to you as homework. And we to compute the probability along with the number of reflexive relations, I also need to know the number of total relations possible. Now total relations possible is simply 2 to the power 9. I again let you work out the details. Therefore the probability would be 2 to the power 6 over 2 to the power 9, or 1 over 2 to the power 3, which leaves me with 0.125 as the answer. Okay, so here is another question. Once again, after reading this question, please pause the video and try to attempt this yourself. Let R be the set of all binary relations on the set 1, 2, 3. Let's say set A equals 1, 2, 3, and I'm interested in all binary relations on this set. So meaning 1R1, 1R2, 1R3, and so on could be in R. So suppose a relation is chosen from R at random. The probability that the chosen relation is symmetric is what? So this time the only change in the question is we are moving from reflexive to symmetric relation. Uh, Once again, pause the video here and try to solve this yourself. Let me move on now with the solution. So before we uh, solve this problem, we need to understand what a symmetric relation is. A symmetric relation, so for a symmetric relation, here is an example. If A is 1, 2, and 3, then R contains 1, comma 1, 2, comma 1, 3, comma 3, 1, comma 2. This is a symmetric relation on A. Why is this a symmetric relation on A? Let me show you another example. R containing 1, comma 1, 2, comma 2, 3, comma 3, 1, comma 2, 2, comma 1 is also a symmetric relation on A. By now, you must have recalled what a symmetric relation means, but if not, then here is the general definition of a symmetric relation. If A comma B belongs to R, then B comma A must also belong to R. Then the relation becomes symmetric. So if 1 comma 1 belongs to R, then 1 comma 1 is by default symmetric. So if 2 comma 1 belongs to R, then 1 comma 2 should also belong to R. Remember, these are ordered pairs, so the order matters. So if 2 comma 1 exists, 1 comma 2 should also be there. So that's what makes the first relation symmetric. Now let's take the second example. So 1 comma 2 exists implies 2 comma 1 also exists. That's why the second one is a symmetric relation. So now that you understand what symmetric relations are, can you find out the probability of choosing a symmetric relation by random? Um, okay, so once again, we understand how to compute probability. So we first need to compute the number of symmetric relations possible. We know from our understanding of symmetric relations that 2 to the power of n into n plus 1 by 2 times. So that means symmetric relations are possible, or 2 to the power 6 symmetric relations are possible. And total number of relations we have already worked out, it's 2 to the power 9. So the answer still remains to be 0.125. So now we know the number of reflexive relations, irreflexive relations, symmetric relations, antisymmetric relations. But at this point, I should warn you that antisymmetry is different from asymmetry. So number of asymmetric relations is different from number of antisymmetric relations here. Uh, uh, we will not get any more into uh, the basics here, but these are a few things that you should know uh, uh, at this level for this course. Uh, don't bother to memorize any of these formulae. Usually, I never test my students for their memory skills. So for your exam, usually you're allowed to carry a cheat sheet, and if it's a remote exam, you would obviously have access to these slides. So don't worry about memorizing them, but rather ask yourself how possibly um, uh, these formulae explain uh, or how would you count, let's say, symmetric relations and why it turns out to be n times n plus 1 over 2 possibilities there. At the moment, we don't know how to generalize for transitivity, so you are saved from there. So let's summarize the story so far. We understand what a relation is, and we see that a subset of a Cartesian product, which is a relation, is a very interesting uh, and applicable thing when it comes to capturing interrelated data. So we love to see the data that we have as a relation. So that's the fundamental idea that we are trying to develop. So here is an example. Here is an attendance relation. So student ID 1, attended session ID 1, student ID 2, attended session ID 1 can be now captured as a relation. Um, Please go ahead and install MySQL and RDBMS, which we would explore in this course. We'll come back to RDBMS in more detail in later parts of this course. And we uh, solved a few problems or dig a little deeper into this idea of relations purely with the objective of getting ourselves acquainted with this idea or familiar with this idea of relations. Let's stop here for the day, and when we come back, I have some more interesting things for you. Bye.